Solving an absolute value equation. Before we go over these three examples, let's remind ourselves what is the definition of the absolute value. Definition of the absolute value of x. It's actually a case-by-case definition, which really helps the logic for a computer scientist. A lot of times, a computer scientists write case-by-case logic. Case 1. If x is greater than or equal to 0, then the symbols called absolute value of x is simply equal to x. Case 2. If x is less than 0, then the symbols absolute value of x is equal to the opposite of x. So we don't usually say negative. It's better to just say opposite of x. All right. Taking this case, we could actually create a shortcut. So a shortcut here would be and the shortcut is for solving equations, solving an absolute value equation. Solve the absolute value of x is equal to some constant a. What you could write next, on the very next line, is actually x is equal to plus or minus a. Because it's really a case situation. So you either have case 1 or what? Or you have case 2. That's a comma. So when we read this, we really should say what? Positive or negative a. Or you could say positive or opposite of a. All right, let's go ahead and use this shortcut. So for example A, divide the entire sides by -2. Absolute value of u is now equal to 7. The very next line, you'll write u is either positive or -7. Best way to write it is obviously write the English symbols. So you could actually write the word or. So either one of these is acceptable. Example B. What if you divide the entire sides by -3? Could you have the absolute value of w is equal to -9? Well, this is not possible. There's no solution here. And finally, the last one here, subtract 9, and we get the absolute value of y is equal to 4. So y is equal to 4, or y is equal to -4. Oh, I forgot to mention in the previous example why there's no solution. When you take an absolute value of a number, it can't be negative. So the absolute value of w is equal to a negative number. This is actually a false statement. So I should indicate here that this is false. There's really no such thing. In other words, these mathematical symbols are false, and so there are no w values that will satisfy that absolute value equation. And the equation I'm talking about is the original one. There's no W values that will actually satisfy this equation. Solving an absolute value equation. Solve for x. The absolute value of 3x minus 9 is equal to 6. Let's recall the shortcut. If you have this type of absolute value equation, absolute value of x, let's use capital X, is equal to some constant b, the next line you would write is the absolute value of x is equal to b, or the absolute value of capital X is equal to the opposite of b. That's what we're going to apply here. And then I'll show you a alternative solution as well. Let's see. Okay. So the next line we're going to write is 3x minus 9 is equal to 6, or 3x minus 9 is equal to negative 6. And so we really just solve these two separate equations, and then we'll put the or in between the answers. So we have 3x is now equal to 15, divide the entire sides by 3, x is now equal to 5. Or what? Well, we could add 9 to both sides of this equation, and we get 3x is now equal to 3, and you could divide the entire sides by 3, and you get x equals 1. So the final answer is x equals 5 or x equals 1, and of course you could check your answer by checking the original equation. Put in 5 in there, take the absolute value, do you actually get 6? And so on and so forth. Put 1 in here, and then simplify the expression, take its absolute value, ask yourself, do you get 6? And you do. I actually did the check in my head. I'm going to circle this as a final answer. And now I'm actually going to show you an alternative way to do this problem that requires some absolute value properties that you would run into in a calculus course. So let's say if you have absolute value of m over n, here you could actually say the absolute value of m over the absolute value of n, as long as n is what? N is not 0. Okay, so that's one property. Here's another property. What if you have the absolute value of p times q, and p and q are real numbers here? Well, that's equal to the absolute value of p times the absolute value of q. And that's what we're going to use for this alternative solution. So let's start once again with the absolute value of 3x minus 9 is equal to 6. And some of your algebra instincts will lead you to think, or lead you to factor, the 3 inside the absolute value. And so you get that. And now we'll go ahead and use this property. The absolute value of a product is equal to the absolute value of the first factor times the absolute value of the second factor. All right, let's take the absolute value of the first factor. Absolute value of 3 times the absolute value of the second factor. And of course, the absolute value of 3 is 3. So I'm going to divide the entire sides here by 3. And we get the absolute value of x minus 3 is now equal to 2. And notice this is very different from the solution that was presented here on the left. But let's see what we get now. X minus 3 is equal to 2, or x minus 3 is equal to negative 2. So x is equal to 1, or x is equal to 1. Of course, I miscounted. What's 2 plus 3? 2 plus 3 is not 1. 2 plus 3 is 5. How about that? There we go. And notice, we do end up getting the exact same answers. So the journey was a little different, but it worked out just as beautiful. Solving a quadratic equation using the square root property. What is the square root property? The square root property goes something like this. If you have a quantity squared and it's equal to some constant, then when you take the square root of that quantity squared, you also have to take the square root of the other side. There's a few things you could write here, but the definition of m squared is really absolute value of m. And then we equal to the square root of b. So we can certainly take that approach. And then, of course, how do you solve a absolute value equation? Now we would write m is equal to plus or minus the square root of b. Why don't we use that approach for this problem, and then I'm going to actually check the problem using a alternative method as well. So here's a quadratic equation, but it is instructed to use the square root property. So let's make it clear. I'm going to use the square root property here for the first method, and then we'll try something else for the second method to check the answer. U plus 1 quantity squared. Let's add 36 to both sides, and here we go. We can now take the square root of this side and the square root of this side, but the square root of a quantity squared is now the absolute value of that quantity, which is equal to square root of 36. And then how do we solve the absolute value equation? No problem. U plus 1 is now equal to plus or minus the square root of 36, which is 6. Now we're going to we're going to subtract 1 from both sides. So we have u is equal to 5, or u is equal to -7. Let's use an alternative method to check our answer. The alternative method I'm going to suggest is actually factoring. We could factor this. So method 2, just to give some variety here, u plus 1 quantity squared minus 36 is equal to 0. Well, that's just a difference of 2 squares. That's a squared minus b squared, which we know is the factor a plus b times the factor a minus b. Let's write that instead. So for the next equation, we're going to have u plus 1 plus 6 times u plus 1 minus 6 equal to 0. Therefore, u is equal to -7, or u is equal to, let's see, that says subtract 5, no, positive 5. There you go. Notice you get exactly the same answer. Pretty cool, huh? So here are a couple of quadratic equations, and if you look at them carefully, they're not factorable. They're not going to be easy to factor. So why don't we try a different approach? Why don't we complete the square? Complete the square, and we'll write the answers in the form of exact answers. Let's start by moving this 66 by subtracting 66 to both sides of the equation. And we're going to have x squared minus 18x. And then we'll have a blank space here. Is now equal to -66. And in that blank space, we're going to complete the square. We divide this 18 by 2. We get 9. You take 9 and you square it. So you're going to add 81 here. When you add 81 there, you got to balance both sides of the equation. You add 81 over there. Now, why do we complete the square? This factors really nicely. That's x minus 9 quantity squared is now equal to 15. Now, we know how to solve these equations. Use the square root principle. Now we have the absolute value of x minus 9 is equal to the square root of 15. How do we solve absolute value equations? The next line, you will write x minus 9 is equal to plus or minus the square root of 15. And then finally, add 9 to both sides of the equation, and we write x is equal to 9 plus or minus 15. I'm sorry, square root of 15. So x is equal to 9 plus root 15, or x is equal to 9 minus root 15. Go ahead and do example B on your own. You could pause the video, and then if you need to, play the video and check your answer. So you have x squared plus 2x is now equal to positive 5. Once again, let's complete the square on the trinomial over here. Well, actually, it's a binomial right now, but after completing the square, it will be a trinomial. Take 2, divide by 2, you get 1. 1, square it, we're going to put it right here. 1 squared is 1, so we're simply going to add 1 to complete this square. Now we could factor is equal to 6. And use the square root principle. We now have the absolute value of x plus 1 is equal to plus or minus square root of 6. Oh, sorry, I take that back. Square root of 6. Now, how do we solve an absolute value equation? We write x plus 1 is equal to plus or minus root 6, and then subtract 1 from both sides. And notice we get x is equal to negative 1 plus root 6, or x is equal to negative 1 minus root 6. And let's circle our exact answers. Those are our exact answers. Applying the quadratic formula. Use the quadratic formula to solve for x. First thing you want to do is write the quadratic formula. The quadratic formula is actually an if-then statement. If we have ax squared plus bx plus c is equal to 0, big comma, big comma, big comma, then we have a formula for x. It's x equals opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. Notice we do have the first part of that if-then statement. We have the first part of that sentence. We do have ax squared plus bx plus c. Why don't we label everything? A is 4, b is equal to negative 6, and c is equal to negative 1. Let's plug it into the formula. X is equal to the opposite of b plus or minus the square root of the quantity negative 6 squared minus 4 times negative 1 all over 2 times 4. Plus or minus the square root of 36 plus 16. So 36 plus 16 is 52. All over 8. X is now equal to 6 plus or minus. There's a perfect square in 52. It's actually 4. Oh, meant to write 13. And you're reacting to this problem now. And from here, we factor out a 2, and then let's see what's left. We have a 3 plus or minus the square root of 13, and put that over 8. Reduce the factors of 2, and we finally get x is equal to 3 plus or minus root 13 over 4. Oh, we're done. We'll go ahead and circle those two answers. And those are what we call those two exact answers. And the method that we used here is by the quadratic formula. Solving a quadratic equation with complex roots. Find all the complex solutions of this quadratic equation. Why don't we apply the quadratic formula? Remember that if you have ax squared plus bx plus c equals 0, then we actually could use this formula. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. Let's try it. X is equal to the opposite of b, which is 5, plus or minus the square root of the quantity negative 5 squared minus 4 times 6 times 4, all over 2 times 6. Let's see what this yields. The next expression is 5 plus or minus the square root of, looks like 25 minus 24 times 4. What is 24 times 4? 96. So 25 minus 96. Negative 71. So we have negative 71 as our discriminant. Put this over 12. And now we have 5 plus or minus I times square root of 71 over 12. Let's write our answers in a plus bi form. Therefore, x is equal to 5 over 12 plus root 71 over 12 times I, or what? Or x is equal to 5 twelfths minus root 71 over 12 times I. So that is what we mean by a plus bi form for a complex number. Different kind of a and different kind of b. Let's use capital A and capital B, I. So that is the standard form of a complex number. Let's circle our two complex answers. And if you want to pause the video now and try to do part B, feel free. And then you can unpause it to check your answer. Negative 5 plus or minus 25 minus 52. What is 25 minus 52? Let's see. 27. Negative 27. Square root of negative 27 all over 26. And of course, you're going to simplify this. X is now equal to negative 5 plus or minus, that really says I times root 27 all over 26. And of course, you could simplify the square root of 27. There's a 9 times 3 in there. So x is equal to negative 5 plus or minus 3 root 3 times I all over 26. Let's write our answer in a plus bi form. X is equal to negative 5 over 26 plus 3 root 3 over 26 times I, or x is equal to negative 5 over 26 minus 3 root 3 over 26 times I. Solving a rational equation that simplifies to a quadratic. Technically speaking, this equation has a rational function plus a constant function is equal to another rational function. Remember that in rational functions, you have to pay attention to its domain because there are definitely some domain restrictions here. There's a domain restriction here and a domain restriction here. Let's write those out. We know that u minus 2 can't be 0. So u cannot be or cannot equal 2. U cannot equal 4 as well. So I'm going to go ahead and circle that just to make sure we don't run into problems later. Now, to solve this equation, we want to first eliminate fractions by multiplying by the lowest common multiple of all the denominators. So notice right here, this has a denominator of this right here, this constant term has a denominator of 1. So it's really the lowest common multiple of u minus 2 and u minus 4. Let's take those two factors and multiply both sides of the equation by those two factors. On this side, we're going to multiply by u minus 2 and u minus 4 as well. I'm going to put a bracket, I guess, or parentheses, either, oh, excuse me. Let's try it right there. Could change this to parentheses as well. Okay, we're ready to simplify. We get u minus 4 times the quantity u minus 1 plus u minus 2 times the quantity u minus 4 is now equal to u minus 2 times u minus 6. And what do we do from here? Well, naturally, you'll react to this problem and just multiply all these binomials together. We get u squared minus 5u plus 4 plus u squared minus 6u plus 8 is now equal to u squared minus 8u plus 12. And as usual, you're going to collect like terms and try to set this quadratic equation equal to 0. What do we have here? We have u squared. We have negative 11u right here, negative 11u, add 8u. So minus 3u. And we have a 4 and an 8. 4 plus 8 is 12, and then subtract 12, we get 0. So we're in good shape here. Equal to 0. Isn't that pretty? Equal to 0. I'm trying to line up my equal signs. That way I'm pretty neat. U times u minus 3 is equal to 0. So u equals 0 or u equals 3. And notice these do not coincide with our domain restrictions, so we can circle this as our final answer. And you're always welcome to check this on your own. And if you wanted to perform a check with one u value at a time, you would just put it in the original equation and see if it is showing that one value is equal to another value. Solving a rational equation that simplifies to quadratic. factorable quadratic denominator. We have an equation here that's made up of two rational functions on the left side of the equation. Here's one, here's a second one, and there's a third rational function right here. Remember, for rational functions, we always have to pay attention to the denominators first, because there are often domain restrictions. If we look at this one here, there's a nice pattern that's going on here. Let's write that out. We know that denominator, w squared minus 9w plus 20, cannot equal 0. Now, this quadratic expression on the left is factorable. This is w, 5, 4, subtract, subtract. And notice w can't be 5 and w can't be 4. One of the rare times that we actually write an and here because of the not equal symbol. Naturally, you write and because we don't want either of these w's. All right. Now we're ready to actually solve the equation. Let's use the lowest common multiple of all the denominators. In this case, it's simply w squared minus 9w plus 20. So if you do that, let's multiply both, excuse me. Let's multiply both sides by w squared minus 9y plus w. And on this side, w squared minus 9w plus 20. And then simplify and reduce. So for this first factor here, when you distribute this quantity to this one, a w minus 5 factor will cancel out. So we're left with 3 times w minus 4. For the next part, we're left with plus w times w minus 5. And then finally, on the right-hand side of the equation, we simply get negative 4. Now this problem is a little bit simpler to react to. Let's collect like terms. We get w squared. We have 3w minus 5w, so we have minus 2w. We have negative 12 on this side, and let's go ahead and add 4 and set it equal to 0. What do we have here? W squared minus 2w minus 8. Ooh, these have nice patterns. Looks like this is factorable. Let's try factoring. W times w, w and w. We have 4, we have 2, we have subtract 4, add 2. W is equal to 4, or W is equal to negative 2. There's a problem here, obviously. So what is our final answer? Well, remember that W can't be 5 and W can't be 4. So the only correct answer here is this one. W can equal negative 2. And if you don't believe me, you can always go back, take this 4 and plug it into the original equation and see what happens. And then, of course, take this negative 2 and plug it into the original equation and see what happens. Well, obviously, if you put 4 in the denominator here, we get into a lot of trouble. We're not allowed to divide by 0. So you can see that the final answer is W is equal to negative 2. Remember to show your work. Be very neat throughout. Solving a radical equation that simplifies to a quadratic equation. Let's solve this radical equation. We're going to solve for y. One way to balance this equation is apply the function x squared. So if we apply the function x squared to both sides, that really means square both sides. I'm going to go ahead and square both sides. And when you square both sides, what do you get next? You get negative 9y plus 45 is equal to y squared minus 10y plus 25. This is a quadratic equation. You want to set this equal to 0. Let's try this. Let's put the 0 over here. Y squared. And then we have negative y. And then subtract 45, so negative 20. Ooh. I'm going to factor this quadratic expression on the right and then turn the equation around so that we get y. We get the factor y minus 5 times the factor y plus 4 is equal to 0. Make sure you check your factoring. Always check to make sure you're 100% correct. And then we realize that y is equal to 5. Or what? Y is equal to negative 4. Now, for radical equations, you always have to check. So we're going to go back to the original equation. We're going to check the original equation. Let's perform that check. So remember the original equation is right here. It's the square root of negative 9 times y plus 45 is equal to y minus 5. So we're going to take that original equation and we got to check it. Let's take y equals 5 and we're going to check it for this expression. Negative 9 times y plus 45. Is that in fact equal to? Well, let's figure out what it's equal to. Negative 9 times 5 plus 45. That is equal to the square root of 0. Is that equal to 5 minus 5? Yes, it is. Yeah, which is equal to y minus 5. Yes, we've actually checked it. We've checked. That check makes sense. Why don't we check y equals negative 4 with the original equation? So we take negative 9 times y plus 45. And we're going to evaluate this at negative 4. Negative 9 times negative 4 plus 45. What do we have here? We have 36 plus 45. That is 81. What's the square root of 81? It is 9. Is 9 equal to, negative 4 minus 5? And the answer is, whoa. No way. This is false. This is absolutely false, right? There's no way 9 can equal negative 9. So this checking over here is explaining to you that y equals negative 4 is not a solution. Okay, it's not a solution. What is a solution? Y equals 5. So even though I'm circling the final answer over here, there's a lot of work to be shown for these types of problems. I'm going to circle the entire page. You got to show all this in this particular order as well. And so that's the work that needs to be shown. We're going to attempt to solve this radical equation. There are actually two radicals, right? Here's a radical function. Here's another radical function. And then it's equal to a constant function. The procedure for one radical in a radical equation is to isolate a radical on the left-hand side. Why don't we do that? Why don't we add this radical over here to both sides? And let's see where that takes us. Now we square both sides. We're going to apply we'll apply the function x squared to both sides of the equation. And remember, x squared is often a 2-to-1 function. And so it's very likely that it could produce an extraneous solution. So we have to be careful of that. We have to be aware of that when we apply the function x squared to both sides. Now we react to this. We react to this by saying this is 6y plus 31 is now equal to 4 plus 4 times the square root of 2y plus 19 plus the quantity 2y plus 19. I'm going to take the parentheses off of the 2y plus 19, even though they're invisible. They aren't really there, so that I could collect like terms a little bit quicker. Now we isolate the radical again. This time the radical is on the right. It's okay to leave it there. Let's subtract what? 23 from both sides? If you subtract 4y and then plus 8. Actually subtracted 2y from both sides as well. Is now equal to what? Equal to 4 times the square root of 2y plus 19. We could divide the entire sides by 4. Notice there is a common factor on the left-hand side of the equation, so we could reduce. Let's show that common factor. There it is. Is now equal to the square root of 2y plus 19. Go ahead and square both sides. And if you square both sides again, we're left with y squared plus 4y plus 4 is now equal to 2y plus 19. This is really nice. Y squared plus 2y minus 15 equals 0. And this is factorable. The quantity y minus 5 times the quantity y plus 3. Oh, that's incorrect. I checked my factoring. Check your factoring. Always check while you're doing it. That should be y plus 5, then y minus 3 is equal to 0. So y is equal to negative 5 or y is equal to 3. Is it really? How do we know for sure y is equal to negative 5 or y is equal to 3 when you actually performed x squared to both sides of the equation? When you perform x squared to both sides of the equation, you might get something called an extraneous solution, or really it should be described as an extra number. Let's make sure we don't have any extra numbers. And the way we do that is we check the original equation. Let's check the original equation and see what happens. What we're going to do is check this original expression here. 6y plus 31 minus the square root of 2y plus 19. Let's first check y equals negative 5. For y equals negative 5, we're going to perform this check. Take that expression and let's see what it works out to be. 6 times negative 5 plus 31 minus 2 times negative 5 plus 19 is equal to 1 minus the square root of 9. Well, that is 1 minus 3. And what do we know about 1 minus 3? That's equal to negative 2. However, that is not equal to what? To positive 2. Notice there's a positive 2 in the original equation. That does not equal to positive 2. What does that mean? Therefore, the original equation is not satisfied, and therefore y equals negative 5 is not a solution. So we cannot copy that. I mean, we cannot circle that. Why don't we check the other number? Why don't we check y equals 3? For the original equation, take the square root of 6 times 3 plus 31 minus square root of 2 times 3 plus 19. And let's see what happens to that expression. We get 18 plus 31, that's the square root of 49, minus 6 plus 19, minus the square root of 6 plus 19, which is the square root of 25. That's 7 minus 5. Wait, that does in fact equal to 2. So this is true. We do have an original true equation. Therefore, what is our final solution and our final answer? Y does equal 3 for this original equation. I'm going to circle that. That is the final answer. But make sure you can show all your work. So I'm actually going to circle the entire page. Because all your work is the evidence that you need to display.